Good morning, everyone. Welcome back. This is Dr. Quinton speaking. I hope everyone enjoyed the lab that you guys performed. I do apologize for any confusion from the slides that I had the teacher show you, in a conclusion for the experiment. If you do have any questions about it, we can discuss it when I get back. In the meantime, we're going to continue learning a little bit more about the heat. So we're going to start the main unit on thermodynamics. All right, it's a big word. You probably heard it before. So let's break it down. So thermo means heat. Dynamics refers to something changing. So in this case, thermodynamics studies the changes in heat. Or as I like to say it, we're going to learn how to follow the heat. Bring on the heat. But before we get to the notes, your teacher is going to have you watch a video on heat. You'll probably enjoy it. This is going to be a Bill Nye video. But while you're watching, you will have an assignment to complete as you watch the video. There are certain points or words that you'll need to keep track of as you go along. So make sure you pay attention. And then when we are done with the video, we'll come back to the notes. All right, you guys enjoy the video. Teacher, you can pause these notes now, please. Hello, everyone. Welcome back. So I hope you enjoyed the video. And as Bill Nye said, all objects have heat. Heat is simply the movement of molecules. In this case, heat would be the random motion of particles. For an example here, remember heat is simply a form of kinetic energy. So when we talk about heat, we're talking about the kinetic energy, for example, of the gas molecules in a container. Now, since heat is a function of the amount of movement of molecules, then that means that the movement of the gas molecules reflects the amount of heat in the gas. Therefore, if there's more heat in those molecules, then the faster they will move. Now, I did want to tie this in to what we've been talking about before, so I wanted to bring you back to this slide. It's always important to remember, heat always flows from hot to cold. So energy is always going to flow from a region where it's concentrated or there's a lot of it to a region where it's not, or to where it's not, where there's not a lot of heat. So heat always flows from hot to cold. Now, as we saw from the Bill Nye video, we know that there are three ways in order that heat can change, from when it moves from one place to another. So we know that there is conduction. This involves heat moving through some sort of solid material, where the atoms or molecules are packed closely together. There's convection, which involves the change of heat with either a liquid or a gas, so hot air rises. And then there's radiation. That doesn't require any sort of medium at all, but the heat travels in waves through space in order to move from one place to another. Okay, now to tie these two ideas together, so we gave the example of ice melting. So heat always flows from hot to cold, so ice feels cold to the touch because energy is flowing from your hand into the ice. That means your hand has more energy than the ice does, so it flows from your hand to the ice. And if you're touching the ice, then that would be conduction, because you have two solid objects, the heat flowing from your hand to the ice by way of your hand through your skin molecules. Likewise, fire feels hot to the touch because energy is flowing from the fire into your hand. If something feels hot, then it means that energy is flowing from whatever that object is into you. And in this case, you would feel the heat because of radiation. There's no direct contact between you and the fire, but the energy is transferring through the air by waves reaching your hand. Now, we have already seen energy transfer in chemical reactions. That was what your lab was about a couple days ago. So, chemical reactions involve energy transferring or moving between different compounds because we're either going to have molecules being broken or bonds being broken or bonds being made. And this is going to involve either the absorption of energy or bonds being broken or the release or giving off energy when bonds are being made. Now, one type of thermal energy transfer that you witnessed during your experiment were endothermic reactions. Now, these are endothermic, means heat going into, so that means the reactions were taking in or absorbing heat energy from the surroundings. In this case, in terms of the experiment, the surroundings would be you, because you're separate from that. So when you touch the object and it feels cold, that means energy is going from you, from the surroundings, into the reaction. So endothermic reactions, because of energy being absorbed, these cause the temperatures to fall, so they feel cold to the touch. And this reflects the fact that more bonds are being broken than are being made. Conversely, we have exothermic reactions. Exo means out of, so for exothermic reactions, these give out heat, so they feel hot to the touch, because what you're touching has more heat than you do. Heat always flows from hot to cold. So they feel hot to the touch. And this reflects the fact that more bonds are being made than are being broken. When we want to show the relative difference in the amount of energy between the reactants and products in a chemical reaction, we use what's called an energy level diagram. Now, for the case of endothermic reactions, the product ends up having more energy than the reactant because energy is being absorbed. So the line shows us the amount of energy in the reaction at any given time. So that means that relative to the reactants are absorbing energy until we reach a certain point where now the reactants have enough energy in them so that when they do hit each other, they can break the old bonds and then form their product. So the activation energy is all the energy that is being absorbed in order to make the product, and then all that energy that is being absorbed is being stored in the product. With exothermic reactions, which feel hot to the touch, we still have a certain amount of energy that needs to be absorbed in order for the reaction to happen. So we still need the reactants, the molecules, to move and hit each other with a certain amount of energy. But once that happens, then that means all the energy that has been saved in the reactant is now going to come out, and when we're done, the product will have less energy will have less reactants. That's the reason that these feel hot to the touch. Well, that heat has to come from somewhere. And since the reaction feels hot, that means it's giving off energy. And where's the energy coming from? Well, you're only starting with a certain material, and that's reactants. So therefore, when this reaction feels hot, all the energy is coming out of the reactants, so that all the heat you feel, and then the product ends up having less energy than reactants, because all the energy is being lost as heat. Now, from here going forward, we're going to consider heat to mean one of two things. Heat will either be the amount of thermal energy or kinetic energy contained in something, or it can be the amount of thermal energy that's being transferred into or out of something. So if something is holding a certain amount of energy, then it means that a certain amount of energy had to go into it, and it also reflects the amount of energy that can come out of it. Now, one more word about temperature and heat before we move further. Most everyone has a certain understanding about heat and temperature. In fact, a lot of people still get them confused with one another. But it's a good idea to try to keep these separate because it's going to help us understand what we're going to see in the future. So remember, if something is hot or cold, then we know that it contains a lot of energy if it's hot, or it has a small amount of energy if it's cold. Remember, we're referring to heat as the amount of energy in something, or the amount of energy that it's either going to be able to absorb or give off. So, temperature basically tells us how much energy is in something. Now, this is chemistry, and in chemistry we do quantify things. So that means there is going to be some math involved. I can almost hear the groans from here. But just keep in mind that heat is a form of energy. Now, what we use, the SI unit, or the International System Unit for heat, is what's called joules. And this is derived from the units that are used in order to create force and work. We'll get to that in a little while. Just right now, I want you to know that the unit that we use when doing most of our calculations is in joules. Now, more common in thermodynamics is the word calorie. Now, you're familiar with calories. You've probably heard about them since you were young. Now, by definition, 1 calorie, abbreviated CAL, this is the amount of heat that's needed to change the temperature of 1 gram of water by 1 degree Celsius. So that means if you had 1 gram of water, which would be like 1 milliliter, and you put a heat into it in order to change that amount of water by 1 degree, the amount of heat would be equal to 1 calorie. Now to relate calories and joules, this is our conversion unit here. So 1 calorie equals just a little over 4 joules. Now, as I said before, you've heard of calories before, but what you may not know is that when you're talking about food calories, what you're actually talking about is 1,000 of these little calories. So when something has, say for example, if we had like a bag of chips, and altogether it would contain like 500 calories. Well, actually that would be 500 big calories, or that'd be the equal, pretty much the equal of 500,000 little calories. So most of the time when you're hearing someone say calories in food, they're talking about big calorie, which is the same as 1,000 little calories. We'll get more into this later on. Okay, we are up to our first seed question. And our question is, why can you put your hand in a 400 degree Fahrenheit oven and not get instantly burned? You know, just holding your hand in the oven without touching anything. But if you do happen to touch the metal rack, you do get your hand burned. All right, teacher, I would like you to pause the presentation for a moment, for about a minute, let the students discuss it, and then we'll come back together and hopefully you can call on some people to get their answers before we resume the presentation and find out what's going on. All right, so go ahead and pause the video now, please. Okay, we're back. Now, first of all, I want you to think about the fact that right now, it means both the air and the metal inside the oven are both the same temperature, 400 degrees Fahrenheit. So that means that the molecules in the air and in the metal, the rack, are moving at the same speed. But why is it that when you put your hand in the oven without touching the metal, you don't get burned, at least not immediately, but if you do touch the metal rack, you do? Well, the reason is because even though the air and the rack are at the same temperature, the molecules move in the same speed, they have different amounts of energy. So the reason you get burned by touching the metal is because there's more energy going into you than there is coming from the air. Now that brings us to the first concept of thermodynamics, the concept of what's called specific heat. Now first of all, just something that you've probably seen before. You've probably seen before, it's easy to change the temperature of some things. For example, air. It's not hard to change the temperature of it, but you may also have seen that it's kind of hard to change the temperature of others. For example, water. It's easier to warm up the temperature of the air than it is to warm up the temperature of the water. It takes more energy in order to warm up the water. Now the relationship between the amount of energy that you have to add to something and the change in its temperature by a certain amount is given by this equation. This is described as Q equals mc delta T. Now the Greek letter delta just means the change in something. That means it's going to go from one value to another. And we're going to need that in our calculations. Now we find out how much there is of something by measuring its mass, and that is the symbol m. C is called the specific heat capacity. This is how much heat something can absorb, and the value of C depends on the material that you're using and the units that are used. We'll show in just a moment. Now here we're showing delta T as a change in temperature, so that's going to be equal to the ending temperature, whatever you end up with, minus the beginning temperature. So delta T is equal to what we're ending up with minus what we start with. Okay, now at this time, the teacher has another small video to show you. There are no notes or anything to take along with this. It's only about 2 minutes long, but I'm hoping that it might make it easier for you to understand this concept a little better. All right, teacher, if you would pause the presentation this time, we'll be back in a moment. Okay, we're back. Now just to go over what the video was talking about. Okay, so at the top of the screen we have our specific heat. Now specific heat is referring to the symbol Q. Q is from the Latin word quantus, meaning how much or quantity. So specific heat is the amount of heat that we're trying to figure out. So the specific heat is the amount of energy that something can absorb or take in before it begins to show a change in temperature. Now remember, temperature is a measure of how fast the molecule is moving. The heat is responsible for the molecules moving. So when something absorbs energy, it then begins to move faster. Only when it starts to move faster will it begin to change temperature. So we're trying to relate how much material something has and the amount of energy it can absorb. So the greater the amount of something you have, the more energy it can absorb before its temperature changes. Now different materials can absorb different amounts of heat before their molecules start to move a lot and they start changing temperature. This is because there are different amounts of force that hold the molecules together as their objects. And in order for them to start moving faster, they'll have to absorb that energy. But different materials have different forces holding them together, so that means it will take different amounts of heat before they begin to start changing their temperature and start moving faster. So the equation at the top, the Q equals mc delta T, basically tells us that the amount of heat something can absorb, the Q, depends on how much of the something that you have, its m, mass, and its capacity or ability to absorb heat, and that is our specific heat capacity. Now the way that we can figure out what the specific heat is of a material is by simply solving that equation, Q equals mc delta T, simply solving it for C. So if you know how much energy is being absorbed, you know how much of the material you have, and you know what the starting and ending temperature is, then you can figure out what the specific heat capacity is of a material. And its units can either be in calories per gram degree Celsius. Calories is a measure of heat, grams is a measure of mass, and of course our change in temperature is going to be in degrees Celsius. Remember, we also have joules as a unit of energy, so the joules, where we can represent the amount of heat. We can also use kilograms, which simply be 1,000 grams as our mass. And again, the degrees Celsius will simply be the change in temperature. Now I want you to keep in mind, remember, by definition, the specific heat of water is 1 calorie per gram degrees Celsius. That means that we define the specific heat of water, the capacity of water, as the amount of heat, 1 calorie, that's needed to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, now this figure shows us different types of materials and their heat capacities, either in joules per kilogram degree Celsius or in calories per gram degree Celsius. Now, it's the same amount of energy, just showing different units. Now, the question that I have for you now is, what pattern do you see in these specific heat capacities? Take a look at the type of material it is, the values that go along with it, and see if you can see if you can explain what the pattern is. The teacher is going to pause this presentation for about a minute to give you guys a chance to discuss, and then she'll call on you for answers. Afterwards, we'll restart the video and see what we get. All right, teacher, pause the video at this time, please. Okay, I guess we're ready for discussion. All right, I hope you'll notice that water has a pretty high heat capacity. Remember, this is the definition for specific heat, the amount of energy it takes to raise the amount of 1 gram of water by 1 degree Celsius. Now you'll notice that some of these other materials like silver, aluminum, copper, gold, metals tend to have low heat capacities. That means that they can absorb just a small amount of energy before they start changing temperature, whereas water can absorb a good amount of energy before it starts changing temperature. Now the reason for that is because there are certain bonds that are holding water molecules together as a liquid. Now there's still some bonds there because it's not gas. They're not moving wildly and they're not far apart from each other. It's water, so it's liquid, so the molecules are somewhat close to each other. Now what this means is there is more energy that are holding the molecules together in water than there are holding the molecules together in these metals. So it doesn't take much energy for them to start moving, whereas to moving faster, whereas it does take more energy for water molecules to move faster. Okay, now at this time, the teacher has an assignment for you to work on related to specific heat. The teacher is going to go ahead and pause this presentation. She'll hand out the assignment to you, and then once everyone has it, we'll restart the presentation. All right, teacher, go ahead and pause the presentation this time. Okay, if I'm back on, that means that everyone has an assignment, and we're about to go over the first question together so everyone understands what I'm asking you to do. All right, so here's problem number 1. So the temperature of 335 grams of water changed from 24.5 degrees Celsius to 26.4 degrees Celsius. How much heat did this sample absorb? And we're also given that the specific heat capacity, or symbol C for water, is 4.18 joules per degree Celsius, per gram degree Celsius. Now that's something we already knew because we saw that in previous notes. All right, so what does this mean? What are we being asked to find? All right, it says, how much heat did this sample absorb? All right, now since we're talking about heat and specific capacity, and we also have grams and degrees Celsius, that means we're going to use our equation Q equals mc delta T. Now, Q is the amount of heat, so that means we're going to be solving for Q. So what that means is we need to find what we need from the prompt to fill in these different variables of the equation. All right, so M is mass. Well, we know what the units of mass is, and those are grams. We know that C is the heat capacity, so we know this value is going to go in place of C, and delta T is going to be the change in temperature. So here's how we set this up. So Q is going to be equal to our mass times our heat capacity times the change in temperature. Now we said that delta T, the change in temperature, is equal to our ending temperature minus our beginning temperature. Now, if we look at this, we're going to see that certainly some of these units are going to cancel. So over here in the mass, we have grams on top. In the specific heat, we have grams on the bottom, so those two cancel. Over here, the difference between the two temperatures is about 1.9 degrees Celsius. So the degrees Celsius and the temperature will cancel with the degrees Celsius and the heat capacity. And then once we multiply them all together, the value we get is 2,660 joules, or 2.66 kilojoules. Now how am I getting this number? Well, there are 1,000 joules in a kilojoule. Kilo means 1,000 times. So that would be 2.66 times 1,000 to get our joules. So these are equivalent numbers. So this would be the amount of heat that would have to be absorbed by this much water in order to raise the temperature from this degree to that degree. All right, well guys, that completes our presentation of notes for today. I'd like you to go ahead and try the rest of the problems by yourself. And perhaps when we come back next time, we can go over some of the other answers to see how you're doing. All right, guys, get to work, and we will talk later. Oh, and yes, you are free to use the calculator on your cell phone if you'd like to. If not, the teacher can make one of my calculators available to you.